Hello, and welcome to Spotlight on Antibodies, a podcast from BioWintron, where we bring you the latest antibody industry trends. This month in April, we'll highlight ATP-dependent switch antibodies, the throughput quality gap in antibody discovery, and multiple myeloma antibody treatments. One of the central challenges in immunotherapy is improving what's known as the therapeutic index, essentially maximizing anti-tumor effects while minimizing toxicity. Typically, antibodies bind their targets wherever those targets are expressed, but that can lead to side effects, especially when the target is also present in healthy tissue. ATP-dependent switch antibodies take a different approach. They are engineered to bind their target only under specific biochemical conditions, in this case, the presence of extracellular ATP. ATP, or adenosine triphosphate, is known as the cell's internal energy currency. But in the tumor microenvironment, which is the complex ecosystem surrounding a tumor, extracellular ATP can accumulate to relatively high levels, often due to cellular stress or necrosis. In contrast, ATP levels in normal tissues remain much lower. Mechanistically, ATP acts as a cofactor in the antibody-antigen interaction. Structural studies suggest that ATP can bind at the interface between the antibody and its target, effectively stabilizing the interaction, almost like a molecular bridge. Without ATP, binding is minimal or absent. With ATP present at tumor-relevant concentrations, the antibody becomes functionally active. This creates a form of spatial selectivity. Antibody activity is preferentially localized to tumor tissue. One example application of this concept is in antibodies targeting CD137. This receptor plays a role in T-cell activation, and agonist antibodies have actually shown anti-tumor potential. However, earlier versions were limited by systemic toxicities, including liver inflammation. ATP switch variants aim to address this. For example, the antibody STA551 has been engineered so that CD137 activation occurs only in the presence of extracellular ATP. In preclinical models, this approach has demonstrated anti-tumor activity across multiple tumor types, while reducing systemic immune activation. In first-in-human studies, ATP-dependent CD137 antibodies have shown a manageable safety profile, along with the signs of target engagement, including increased expression of CD137-related signaling genes and infiltration of CD8-positive T cells within tumors. A similar strategy is being explored for CTLA-4, another well-known immunotherapy target. An example for that would be ROSE12, which is a molecule designed to bind CTLA-4 only in ATP-rich environments. Stepping back, ATP switch antibodies are part of a broader class known as conditionally activatable antibodies. Other approaches include protease-activated antibodies, pH-dependent binding, and redox-sensitive systems. What distinguishes ATP-based designs is that they rely on a non-enzymatic, reversible trigger. Binding depends directly on ATP concentration, without requiring permanent structural changes. That said, the effectiveness of ATP switch antibodies depends on how much extracellular ATP is present, and that can vary significantly between tumor types, and even within different regions of the same tumor. Researchers are now exploring ways to combine multiple environmental triggers and identifying biomarkers that could help predict which patients are most likely to benefit. Over the past decade, antibody discovery has become significantly faster. Technologies like antibody library display, single B-cell sequencing, and next-generation sequencing have made it possible to identify large numbers of antigen-binding sequences in a relatively short time. Now, one of the major difficulties lies in determining which of those candidates are actually suitable for development, not just in terms of binding, but also in terms of stability, manufacturability, and overall performance as drug molecules. This is the throughput quality gap. One area gaining attention is microfluidic screening at the single-cell level. These systems allow researchers to isolate individual antibody-secreting cells in tiny compartments, sometimes droplets on the scale of picoliters, and directly measure the antibodies they produce. Because the secreted antibodies remained confined within these microenvironments, it becomes possible to link genotype and function more closely. In some setups, target cells can even be co-encapsulated, allowing functional assays, such as receptor activation or cell-based responses, to be measured in the same system. At the same time, high-throughput infrastructure continues to expand. Large combinatorial libraries can be screened using techniques like fluorescence-activated cell sorting, known as FACS, alongside sequencing-based methods to track enriched clones. Automation has also improved the downstream workflow. Gene synthesis, cloning, expression, and purification can now be performed in parallel at much larger scales, sometimes within a matter of weeks. However, not every high-affinity binder is a viable drug candidate, which is where developability comes in. Developability refers to the likelihood that an antibody can be successfully manufactured, formulated, and advanced through clinical development. It includes properties like stability, solubility, aggregation behavior, and specificity, factors that may not be so obvious during initial screening but are critical later on. There's increasing interest in bringing these considerations earlier into the discovery process. Instead of selecting candidates based solely on binding affinity or enrichment, researchers are starting to incorporate biophysical and functional criteria at earlier stages. That might include screening for aggregation propensity, expression yield, or nonspecific interactions alongside target binding. Microfluidic systems provide functional resolution at the single-cell level. High-throughput sequencing captures diversity at scale, and early developability assessments add another layer of selection, helping prioritize candidates before significant resources are invested. That interplay between targeting, context, and function is especially visible in multiple myeloma, a field where antibody-based therapies are evolving quickly. What stands out today is not just the number of antibody drugs available, but the diversity of formats and strategies being explored. Monoclonal antibodies are now part of a broader landscape that includes antibody-drug conjugates, bispecifics, and even trispecific constructs. Each of these formats expands what antibodies can actually do in patients, whether that's delivering cytotoxic payloads or actively redirecting immune cells. BCMA, or B-cell maturation antigen, has become a central target in multiple myeloma. But it's no longer the only focus. At the same time, immune redirection, particularly engaging T cells, is becoming as important as direct tumor targeting. And increasingly, the way the antibody is engineered, its affinity, valency, and dosing strategy, is just as important as the antigen it binds. Earlier antibody approaches in myeloma were more straightforward. The goal was to identify a target, such as CD38 or IL-6, and then rely on mechanisms like antibody-dependent cellular cytotoxicity, ADCC, to eliminate tumor cells. These therapies can be effective, but clinical responses have not always been consistent. One reason is that target expression can vary between patients, and even within different regions of the bone marrow. Another is that the tumor microenvironment itself can suppress immune activity. More recent strategies include a focus on antigens that are more selectively expressed on plasma cells. There's also less reliance on passive immune mechanisms and more emphasis on actively engaging immune cells, particularly T cells, to drive anti-tumor responses. Antibody-drug conjugates, or ADCs, illustrate both the potential and the complexity of this approach. Belantamab mafodotin, for example, targets BCMA and delivers a cytotoxic payload directly to tumor cells. Its clinical path, including withdrawal and later reapproval, highlights a key challenge in ADC development: balancing potency with tolerability, especially when it comes to adverse effects like ocular toxicity. This experience has informed newer ADC designs, with attention to linker stability, payload selection, and dosing strategies. There's also growing interest in whether these agents could be used earlier in treatment if safety profiles can be improved. Meanwhile, bispecific antibodies bind both a tumor-associated antigen, such as BCMA, GPRC5D, or FcRH5, and CD3 on T cells. This effectively brings T cells into close proximity with tumor cells, promoting immune synapse formation and cytotoxic activity. One advantage is that bispecifics are considered off-the-shelf therapies. Unlike CAR T cells, they don't require patient-specific manufacturing, which can simplify logistics and reduce treatment delays. However, new challenges are emerging here as well. BCMA remains the most validated target, but antigen escape is being observed. This has led to increased interest in alternative targets, as well as strategies that can address resistance more directly. That's where trispecific antibodies may come in. These formats are still in early development, but they reflect a broader shift towards multi-antigen targeting and more complex immune engagement. Early data suggests that trispecific designs may help address some of the limitations seen with bispecifics, including antigen loss and T-cell exhaustion. Some formats also incorporate co-stimulatory signals, with the aim of improving T-cell persistence and function. Across all of these approaches, one theme is consistent: resistance is shaping strategy. And that's all for this month's antibody industry trends. To learn more insights into antibody drug news, make sure to follow BioIntron on LinkedIn or our website at www.biointron.com. Keep up to date with further episodes from Spotlight on Antibodies by following this podcast.